Okay, here we are, part two for lecture series on Monday, February 27th. We just did a recap of our periodic trends, and now we're going to put that into practice with a little warm-up problem. So I've got a couple of warm-up questions here for us. In general, we're going to be comparing periodic trends for a couple of different species, and we're asked in this question to use what we know about both electron configuration and effective nuclear charge to answer the following questions. So the first question is about atomic radius. So we can look back at our periodic table up here and say, okay, as long as we are looking up and to the right of the periodic table, we should see that we've got larger atomic radius. Oh, sorry. Thinking ionization energy. As we look down to the left, we should have larger atomic radii. Up to the right, we should have smaller atomic radii. But the trends, remember, that I've shown us on the periodic table are trends for neutral atoms. So if you notice in this particular problem, I've given us ions, right? So we're looking at the oxide ion versus the nitride ion. Now, generally speaking, cations are smaller than anions. Because when you're looking at a cation, you've removed an electron, so you now are looking at a valence electron that is typically of a lower energy level, depends on what we're talking about. But if we've removed an electron, right, for a cation, then we have fewer shielding electrons or core electrons. So this will allow us to contract because we feel a tighter effective nuclear charge or a stronger pull from that positive nucleus on our new valence electron. Whereas anions, these are atoms that are charged negatively because they have an excess of electrons. The addition of those extra electrons is adding electrons typically to higher and higher energy orbitals. And in doing so, that is increasing the amount of shielding, which is going to increase the amount of, I just said shielding, it's going to decrease the amount of effective nuclear charge that our valence electron experiences from that nucleus. But if you look at this example here, I've given us not a cation versus an anion, I've given us two anions. So it's up to us to figure out which of these anions is going to have the lower effective nuclear charge. Because remember, the least strong that pull on our positive nucleus against our valence electron is, the larger our atom is going to be. So if we look at oxygen and nitrogen, the first question we can answer for ourselves is, well, are these two elements in different rows on the periodic table? Because we know that certainly just moving down a row, we're adding electrons to higher and higher energy orbitals, and that would give us a good indication of which of these elements has a larger number of core electrons that are going to shield their valence electrons from their nuclei. However, nitrogen and oxygen, they're right next to one another. They're in the exact same row, and they only differ by one proton. So let's look, I think, at an orbital box diagram for oxygen versus nitrogen. So they both have 2s and 2p. So here's our 2s and our 2p, three degenerate orbitals. And if I were to look at just oxygen without it being the oxygen anion or the oxide ion, that would be 2s2, 2p1, 2, 3, 4. And then if I were to make it the O2 minus anion, I would add an additional 2 electrons. The reason why we become the O2 minus anion is because we achieve octet when we add 2 electrons. Now let's look at nitrogen. So that's also 2s2, but instead of being 2p4, it is 2p1, 2, 3. And if I were to make this the nitride ion, and 3 minus, I would have to add 3 additional electrons, which again gives us a nice full octet, right? Count them up. These are our valence orbitals, 2, 4, 6, 8, 2, 4, 6, 8. And when we have these two ions side by side, these are isoelectronic. They have the exact same electronic structure or electron configuration. They're also isoelectronic with the following noble gas, neon, right? Here's oxygen, add 2 electrons, we're at neon. Here's nitrogen, add 1, 2, 3 electrons, we're at neon. Okay, so we know that they have the same number of valence electrons, and they are all in the 2s and 2p. So we're all in the same N. So like I said, we can't think about like core versus not, because if I were to write out, let's say, the electron configuration, instead of looking at an orbital box diagram for O2 minus and N3 minus, this would be the preceding noble gas, which I believe is helium, followed by the valence electrons, which would be 2s2, 2p6, 2s2, 2p6 for both. So they have the same number of valence electrons here and here. And they're also in the same energy level. So then what's going to be the tiebreaker here if all things seem comparable? We've looked at orbital stability, right? We've looked at our electron configuration. We've looked to see if there's any kind of shielding. Let's go ahead and look outright at the number of protons in the nuclei of each of these elements. So remember, nitrogen has an atomic number of, let's go back to our periodic table, 7, right? Am I counting right? 4, 5, 6, 7, yes. And oxygen has 8. These are the number of protons in the nucleus. If I wanted to count the effective nuclear charge for the nitride ion compared to the oxide anion, this would simply be the number of protons in the nucleus minus the amount of shielding electrons. So the effective nuclear charge on nitrogen for the nitride ion is going to be 7 pulling protons, shielding with just the 1s2 electrons from the helium, whereas the effective nuclear charge for the oxide anion is going to be our positive pull on the nucleus, which is our 8 protons, minus our shielding, which again is our 1s2, or 2 1s electrons from our helium configuration, right? Because anything written after our noble gas core can be thought of as our valence electrons. So if I were to calculate the effective nuclear charge for each of these ions, I would see that the effective nuclear charge, or how well these valence electrons perceive the pull of the nucleus in the nitride ion, is 5, whereas the strength of the effective nuclear charge from the oxide ions is 6. So since this is a lower effective nuclear charge, then that means that this is going to be larger. Okay. If you want to, you can think of it in terms of like, oh, well, I've added more relative electrons to nitrogen than I have to oxygen, but that's ultimately the same reasoning that follows here. Okay, B. So we're here. Which atom has the highest first ionization energy? So we're talking about ionization energy. And going back to our periodic table, ionization energy and atomic radius have the inverse trend. The tighter our electrons are pulled toward that positive nucleus, the harder it's going to be to remove them. So we need to think about which of these elements, notice I'm not talking about the ions anymore, but which of these elements is going to have the highest first ionization energy. Now, reminder, it's always a good idea to check both your valence electron configuration versus your effective nuclear charge. So we've already done our effective nuclear charge calculations down here. So if I were to expect which of these elements just based on effective nuclear charge would be easier to ionize, it would be the one that had the larger radius. So from effective nuclear charge alone, we would predict that nitrogen would have the lower first ionization energy, whereas oxygen would have the highest. However, we do need to make sure that we are not looking at removing electrons from stable orbitals to confirm this trend. So let's look back at our orbital diagrams, and now we're going to be looking at nitrogen and oxygen unionized. So 2s, 2p, 2s, 2p. Okay, so the electron configuration of nitrogen is this is oxygen, 2s2, 2p1, 2, 3, 4. Nitrogen, 2s2, 2p1, 2, 3. Uh-oh. What do you notice about this valence orbital of our nitrogen ion? Notice each of these p orbitals is half full, which means this is quite a stable electron configuration compared to oxygen, which has only 2 half-full electrons instead of every orbital being either full or half full. So what we actually see here is that the stability of this electron configuration wins out over the relatively small difference in effective nuclear charge, meaning even though we would expect to see ourselves have an easier time removing an electron from nitrogen because it has lower effective nuclear charge, because nitrogen has such a stable valence electron configuration compared to oxygen, it's actually going to be much harder to remove an electron from nitrogen than it is from oxygen. In fact, if we were to remove an electron from oxygen, we would find that we would have full and half full. So that would be even a little bit more favorable, even though it's easier to add 2 than it is to remove that 1. So the answer here is actually nitrogen. So even though the nitride ion had the larger atomic radius, we see that the nitrogen atom itself has the highest first ionization energy because of the stability of this valence orbital. So you always got to check both. Okay, C down here, which is more electronegative, nitrogen or sulfur? So again, electronegativity is similar to this idea of how strong we pull on electrons. The only difference is it's not how strong these atoms pull on their own valence electrons, but how well they're able to pull on electrons that surround them from other atoms as well. So in order to answer this question, I think we should look at both our effective nuclear charges and our electron configurations. So let's go back up to nitrogen. Okay, so nitrogen is here. We know that electron configuration is helium, which is 1s2, and that it is 2s2, 2p3. Now sulfur, notice we're no longer looking at elements in the same row, but we're rather looking at a difference between elements in different columns. Well, okay, different columns and also different rows. So we've got nitrogen versus sulfur. So sulfur is going to have an electron configuration that starts with the noble gas core of neon, and then following 2s2, 2p4. So first, let's do an analysis of effective nuclear charge, ZEFF. Let's do it over here. So remember, effective nuclear charge can be approximated by taking the number of protons that your element has and then subtracting the strength of that positive charge from those numbers of protons by the amount of core electrons that are shielding your valence electrons from that positive pull. So my effective nuclear charge for nitrogen, remember these are all our valence. So I'm going to have for nitrogen, this had 7 protons. Subtract from that again, it's 2, which gives us an effective nuclear charge of 5. Okay, then sulfur. Forgot why I looked up there. I want to figure out its atomic number, which is 16. Could always reverse engineer it, right? This is, let's see here. Let me go back and check. Can I count? 4, 5, 6. Yeah, because neon had 10. Okay, so that is 16 minus the 10 from the neon, right? Neon has 10 electrons, has Z equals 10. So that is 6. Oh, however, gotta be careful here. This is 3s2, 3p4. And because we have, let's see here, 1s2, 2s2, 2p6, more core electrons than we have here, we expect to see a larger degree of shielding. And so, because we have a larger degree of shielding in sulfur, because we've looked down a column, we expect this to have a lower electronegativity because that positive charge is obfuscated or blurred or kind of blocked by this large amount of core electrons. Now, when we're talking about electronegativity, it's not really useful to look at electron configuration because when we're talking about electronegativity, remember, this is talking about elements that are already involved in bonding, which means they've already achieved octet by coming together with some other element. So it's not quite appropriate to look at, like I said, the electron configuration of each atom because it's going to be slightly different when we're talking about atoms that are bonded. So the more electronegative we would expect to be sulfur. Did I just misspeak? I think I did. It's nitrogen, of course. Larger degree of shielding in sulfur. Boom. Okay, you just gotta logic it out based on what we know about electron configuration and effective nuclear charge. That's how this works. So now that we've done a little bit of practice with periodic trends, we are now going to move into an intro to chemical bonding. We're going to define what a chemical bond is, and then I'm going to give you a very brief intro to the different types of chemical bonds being ionic bonds and covalent bonds.